Hello, this is lecture 25. I will continue to describe what tube model does in terms of the several key predictions the tube model produces. And then I will start to switch to our discussion of our new picture by identifying three different forces. These forces are somewhat unfamiliar to us, except for the first one, which is retraction force. That is usually taken to be of entropic origin.
All right. So last time we were supposed to get started on the second section of chapter 16. But I realized this is your only chance. I realized I should go through a little bit more of tube model results because it's a complex theory. So I try to conceptualize what the theory is, what the theory involves, and then I should give you a few results directly. So let me do that. Let me go to the play mode. So it turns out much of the original Doe-Edwards theory, of course, is all summarized in this book. Doe-Edwards has a book called The Theory of Polymer Dynamics. Published around this time. And there's a bunch of mathematics. It's all in their chapter 7. I don't need to go through. It's possible to follow. But what I want to show you is places where you see the several non-monoticities that are discussed in the book, in this model. So it turns out this is the general formula that you deal with. And with that, there comes the first statement. In fact, before that, I probably could give you a sense of it by coming to this page first. So on the upper left is the content. And it's actually quite remarkable that it describes all the nonlinear features like overshoot, like the steady state. They group all that under the title of nonlinear viscoelasticity. Yet, they talk about the stress relaxation separately. They single that out. And I will go through these two parts with you. In fact, in our language, this will be all part of nonlinear viscoelasticity. But actually, it treated this stress after large step strain, actually large step shear, separately, because it was supposed to be a triumph. It was supposed to be an example, some very explicit comparison with data was made. Whereas this later section on overshoot and steady state and non-monoticity is a little bit more qualitative only. So I think this is the reason they single out this to talk about, because they can be quantitative about it. So here's that slide that I want to go to the play mode and show you. So it turns out that there are several topics, as you know. Their theory, of course, is able to deal with everything, including steady state. So this is their steady state result. Don't mind anything else. This is the Q function. in the Q function, the variable is simply Wi, actually. That's what I plotted in my book. Wi in steady state as function of shear rate has a maximum. So it's all in there, okay, in that book. And the second feature, more importantly, I think, is the one I want to show you about overshoot. Okay? So this is a property 2 under the title of nonlinear viscoelasticity, stress growth. Okay? So it turns out that stress growth, if you like, the rest is all simple math, nothing important. If you like, I should not confuse you with anything. I know this is highly confusing, even when I look at it. Remember, this non-monoticity is steady state stress versus shear rate. This has nothing to do with the stress overshoot we do in startup shear, right? Yeah. I want to emphasize that this point is about bar gamma equals 2.2, but of course it happens at the time. You can do this trick, time a tau divided by a tau, and then you get basically Wi T over tau, okay? Okay? So in the limit, when Wi is very large, no, let it be large, okay? Then this 2.2, at 2.2, we call it yield point, right? At 2.2, come on. At 2.2, that's tau y. We call the yield point. You don't call it. You can call it T max. What I'm just trying to show you is that your T max over tau is 2.2 over Wi. So it's much smaller than 1. In other words, this T max occurs at the time scale much shorter than tau in this limit. Yeah? The reason I say that is if that's the case, you can look at the formula, which is the first one. For any time smaller than tau, it's this formula. What is this formula? What is this formula? Let me do one more thing for you. This is, they plotted the so-called transient viscosity. They use shear rate kappa as shear rate. Let me just multiply kappa. Isn't that just the stress then? Of course. But if I have another kappa, you see, I don't know, I don't have the color, but you see, this is the variable of gamma. This kappa times T is also the variable of gamma. What do I recover? You remember gamma H is what? It's the Q function. And that Q function has this feature. So that's how they predicted the stress overshoot. Okay? And according to the Q function, this maximum and going down is all over orientation. So, with this, I explained 2 features of overshoot. I'll come back to the step extension later. Step strength, sorry, the step shear, so-called. Okay, let's see what else I was putting on. I know that I have written something, so it got blocked a little bit. Let me try to indicate the following. So this is the third one. You can still see it. This is the third item, okay, under non-viscoelasticity. This is the third, okay? The third is what? Watch. Steady extensional flow. What does that mean to you? In theory, they can contemplate the idea of steady flow. Don't we just say there wasn't any in experiment? Come on, wake up. Don't we just, in our experiment, when we stretch, nothing, the sample start to break. It never have flow state. Never have steady flow state. No, but in theory, you can always do it. I'm trying to show the great discrepancy between the theoretical effort and the experimental and the understanding coming from experiment. Okay, it's moreover. I'm so sorry. Maybe I should right now. I should come out of the play mode. Okay, so it's all recorded there, and the thing that I not going to say is, oops, sorry, is I'm not. I see. I know what it is. This is the pen from the smart board, which is this the eraser? I guess so. I hope so. Let me do this since we are out here. Let's go to the next page and paste this in. So I can highlight this point. So this is the third feature of the theory. It is unaware of the possibility that things will break up because of the horse race, because of the localized failure, localized yielding. We have not talked, experimentally we talked all about it already, all the stretching. But theoretically, we are not aware of such a thing, so they computed steady state. They just think steady state is possible. And then it's quite amusing to see, look what he says. This formula, which they can calculate, it was in contradiction with earlier studies, earlier data on linear low density polyethylene. Low density polyethylene, that's the long chain branched one. That's the one that resists yielding, that has a hard time going to flow state. And lo and behold, you have trouble because how do you compare? What is your steady state value? So, which basically says, oh, by the way, according to polyethylene results, experimental result, where you arbitrarily take the endpoint as the steady state result, it basically says your viscosity increases with the stretching rate. Okay? Whereas they can only predict a decrease with the stretching rate. And then they commented that, oh, more recent linear response linear polymers seem to be consistent with the theory. So it's, to me, it's already an indication of a big mass, of a big discrepancy between the struggle between theory and experiment. Just my opinion. So let me go to, so we talked about two non-monoticity already. I didn't highlight the consideration story that's in the original paper that was not discussed in their book. So let me just go lastly to their discussion of. I think there's no need to go to play mode anymore. So to the step extension, which you should be most interested in because we spent a lot of time in chapter 12 on this. Which is discussed in a whole section here. And you only need to look at this section. That's where they start to compare their theory with experiment. And this is the two model expression. Look how familiar it is. Okay. Remember, this is just a relaxation modulus, so midge baby stress, of course, which is stress over the strength. This is the equilibrium modulus. So you move this aside. That's exactly the damping function But because, remember, the damping function only accounts for long time after the kink. And this part is the kink. Look, this part is the kink. In other words, this drop is that contribution due to chain stretching that's going to disappear. So you can see that that everything is recovered. In fact, if you multiply a gamma, then you will cancel a gamma there, and what comes out will be the Q function, which has a maximum. So what I'm trying to say, I danced around quite a bit. What I'm trying to say is in the book, when describing the step strength, they plotted G. And they didn't plot Q, which is here. If you plot Q, you would have seen this. And Q, remember, is the stress at long times. In their theory, it would be stress after tau r. So since this was never plotted this way, I would have recognized as soon as I have bought my book in the 90s. We didn't recognize this. So this is the feature of the theory. It shows the kink. This kink is due to this parameter, described by this parameter, showing the loss of stress due to chain retraction, Ross chain retraction, occurring at the time scale of Ross time. And this is the data. The rest is history that one could try to make some quantitative comparison, at least for a subset of data. Okay? So this is just a little more a supplement to what I said last time. I felt it was indeed, I didn't do justice to the Q model. I should say more. And this, there are further development after the book. For example, Mead, Doyle made additional contributions, and Larson, three of them, made additional contributions, I think it was around this time, to take care of the problems, in particular, the problem in the limit of Rawls-Weissenberg number larger than 1. And then subsequently, there's, of course, the grand model, okay, involving several people, Graham, Lippmann, yeah, I want to make sure I know, Milner and McLeish. So this is a 2003 paper. So there are additional improvement, but the whole basic conclusion, the spirit and the construct of the Q model never could change, never changes. Since I mentioned I want to complete this part of the history correctly, I should indicate that for this difficulty of the non-monoticity, okay, this non-monoticity, since this implies shear banding, remember, right? This would imply there's kappa 1 and kappa 2. And since we didn't see it, Professor Pino Marucci made a major suggestion about why you don't have shear banding. And that is this actually never happened. So in his rescue of the Q model, he suggests that you could have this, that there will be no unphysical negative part of it. And the way to do that is to suggest that there is so-called convective constraint release. I think I mentioned it once actually, but okay, known as a CCR. So the idea was the relaxation time, okay, is actually, or relaxation rate is better, is actually quickened, if you like to call it equilibrium, quickened by the fact you are shearing it. Remember, I'm drawing in the rate mode, in the rate, reciprocal of it. So they are claiming that the tube model the chain can escape from the tube confinement because the shear is carrying them out. So in that limit, you don't have this over-orientation because they already got out. So this rescued them so that there will be no shear bending. Well, the sad news is we did see shear bending. So this threw us into confusion, or threw some people into confusion. In fact, informally, I would suggest there are colleagues who suggest, oh, why don't you just go back to the original theory, which I already covered in a book in the chapter 15 that doesn't explain. Okay, so with that, I think I completed what we have in our hands so far. Certainly, given such a thorough discussion of it, you ought to know that that our discovery of shear banding and non-quiescent relaxation does appear to me to be something not easy to explain by the tube model. Let's put it this way. But certainly the concept of structure falling apart is just not so readily, it's not easy for you to dig out that from the tube, from the construction of the tube model. So that's why we moved on to see what's missing, okay, basically. And to see what's missing, there's nothing better than what I drew already here. Take a look at this startup experiment. You got a point where your entanglement no longer act like a cross-linked sample. Since you don't have cross-linking, you only have entanglement. So it looks like entanglement is no longer active anymore, right? By definition. That's why you lose the ability to continue to be elastic. So, so if I do it in a pedagogical way, then the problem is quite straightforward. That is what's missing. In other words, why you start to lose entanglement. This cannot be answered without trying to answer why you could have elastic deformation in the first place, or how could you have retractive force. Well, we very simply says, oh, you have uncrossability, which we call the entanglement. We carefully discussed that. And that will provide you the effect like a cross-linking so that even though I have millions of layers, I can hold only the end layer and shear or stretch and still be able to enact all the deformations at all chain levels. In other words, at the strand level at least. So, the question to answer is the tool that we have. I'm repeating this probably the third time. Why you have elastic deformation? I'm sure every time I do it in a different way. why you had a fine, or you don't even have to say a fine because I'm already saying why you have elastic chain deformation. So of course it's somewhat a fine because it happened that the external macroscopic deformation is translated to local level, to the chain level. So why you have it? So of course that means you need to answer what is causing it. And then when the deformation, I can say it just any way I want, or the chain deformation gives into flow, if you like, or basically ceases, basically. Chain deformation ceases, if you like. If you don't like what I said. When does chain deformation cease? So, so as this is not the first time to draw this picture, and I keep saying this must exist in people's mind for many, many decades. Many, many decades. Remember, whatever I'm going about to answer this question was answered in 2007. But many decades before that, this picture must have been around, this perception of what uncrossability does. So obviously, to answer the first question, it's thanks to these black chains, right? And the black chain is hooked with the next purple chain. The next purple chain is hooked with the next yellow chain, and just keep going, right? I don't have time to draw a million of this, but that's this. So, so what we call that? In other words, what we call that uncrossability. This uncrossability, apparently, if you like, is producing some our original words was something like intermolecular or interchain grip force. Probably in the original paper, I call it gripping force. And basically, it's a grabbing force. It grabs onto the test chain. So hold on. This whole picture is also done at the single chain level. So you may be unhappy, but that's all we can do. And that's all perhaps, at least in the zeros, what we need to do. Is to, again, look at any chain as a test chain, because if you know that chain, what happened to that chain, you know what happened to every other chain, okay? And for that chain, obviously you need to speak about what other chain is doing. So what the other chain is doing, of course, is intermolecular, right? So we don't have, I don't have 10 or 100 hands to show you what all the other chains are doing simultaneously. I'm just going to color one chain red and look at what other chains are doing. So that's what other chains are doing. They're grabbing onto it. And we need to quantify this force. So this acknowledgement of what other chains are doing is a little bit different than introducing the tube concept. A simple way to say it is actually to say that we recognize this force, if you like, is heterogeneous. In other words, you may even call it point-like, because of right? Because this is just a point. So for that reason, the tube model basically smooth out. It was smoothing out the interchain effect, interchain force, if you like. So that's the contrast. So we want to recognize this explicitly in a picture of a chain network, in contrast to the tube model. So, I think that solved the urgency. The urgency is what is causing the elastic deformation to take place. And obviously, the next point, so we give a name. Basically, I think in the book it's called that too. We gave a name called intermolecular gripping force. I think in the paper I have the G in there, but I think subsequently we still have the G there. So there's this force that is producing the chain deformation, producing the chain retraction force. So now let's speak a little more about this. It's all a question of how much we can say about this new force. But the zeroth order picture is this. As I stretch, suppose I have the supply of this force, which is across this valley. I keep drawing. Then we know this force, I know I should probably in red color, is going to increase as I stretch or as I shear. And this is the part that I think I should go follow the book rather closely because some of the notions are, shall I say, notations. Let me use the word notations, are somewhat unique. In other words, I just build up a set of notations that I think is very useful and helpful. So to begin with, let me do this. Come on. There's nothing really more powerful than thinking about startup again. Okay? So the first part would be all that's interesting here for the moment. Let's try to do that. We know, at least if you really do startup, all this part will be quite easy to capture. Why? Because I can say, I'm not going to even worry about the nonlinearity, at least this linear part. This stress is nothing but gamma times plateau modulus. I know in my book I have this as a melt, and for the melt we call the plateau modulus GN0. So basically the plateau modulus that I freely write in here. Here I find it is, not to confuse you, I find it's interesting to share with you a concept between if you like, a elastic notation and a fluid notation. So pretend I have steady state here, which I do. At some long times, I will reach some large strength, I will reach steady state. So how you write that steady state? Well, of course, you write it as sigma, eta, gamma dot, yeah? In steady state, of course. So I just want to persuade you to I can do it either way, in fact. I can do it both ways to persuade you. So for example, this, I can write it as gamma dot times T. And that looks like a viscosity of some sort, called eta plus. So similarly, I can multiply a tau divided by a tau and start to talk about this as modulus and this as Wi. Yeah. Or if you don't like Wi, basically this is like a certain amount of strength. So this is just a side note. I'm just trying to show you on either side, beginning or end, I can have a notion of thinking, writing them either in a fluid notation or the solid notation. Get it? In both regions. So let me now get back to the notations. And let me try to also cover both shear and extension. So shear, I think you quickly accepted what I did here. And for extension, let me just save the space and do it here. For extension, it turns out that you can just use the so-called Neil-Hooking type or rubber elasticity type of if this is true stress, then it's this. And I never, meaning we never find this to be as useful as looking at the tensile force or the engineering stress. So that knocks down 1 over one of the lambda so that this is now linear, essentially linear. Oh, it is linear in this variable now. Oops, what did I do? I know, I just realized something that when we do the recording, my image is on this side. There is the camera on the side, so it's terrible for us to always try to avoid it. So in any case, this is the. I think the only thing to do is to shrink it a little bit. Okay. Any questions? So this is basically, I'm trying to show you both the expression for shear and expression for extension. And I'm going to go on a little more, because what I want to do is to achieve the following, that this phenomenologically written formula for continuum relates nothing about molecular forces. For example, the retraction force. Okay, this retraction force is nowhere in this formula. But I want to make it show up. Do you follow me? There's no molecular forces in these two formula.
You just said that it doesn't account for retraction forces. That's why I was confused.
No, I didn't say. I said basically these formulas is not written in terms of molecular force such as the retraction force. Come on, here all you have is a retraction force, right? But nowhere showing up. I haven't seen. So this is one of the. While I was struggling building the theory, this was one of the things that one must come to overcome to make a connection. So it's very simple. In fact, I don't recall I teach you guys this, but meaning in the class, maybe because we're running out of time. But we did it in physics too. polymer physics too. So this is, I just want to show this. I just want to indicate this is in, because I have students in the class that are not in polymer physics too. So this is this formula. It's completely trivial because well, let me not write it this way because it is P and PL. Let me try to think. The other way around, right? Of course, it's the other way around. It has one P and two L's, so one of the L is there. There's another L. Okay, and this is the elementary amount of force, retraction force, related to the length of the strand. Of course, in terms of end-to-end distance. And what is the rest? The rest is something you guys, I went through with you guys several times. It's the density of strands. So density of strands, whichever way you want to see it, it's the number of these strands per unit volume. Per unit area. We had worked out this before, right? Even in this class, that it's this. Okay, now something magic happened. Did you not see it? Did you not see it? Remember, I just said this formula doesn't have any molecular force showing up. Let me do it. I can only do it that way, actually. Sorry. I can only do it that way because they don't share the same symbol. I just told you guys that this two formula doesn't have any molecular forces involved. Do you now know it has now? It has now because you just need to plug this in. My goodness. What do you get? In my notation. This is the force we're talking about, molecular retraction force. What is it? It is the elemental force. F, ENT stands for entanglement, times gamma. Or times lambda 1 over lambda squared. Okay. We're almost there. You see how simple this is and how powerful it is to understand the concept of this. The density of strands, molecularly, chain level, strand level, and the rest must be the force. And in fact, it is this that inspired me to write that. It was the reverse. Yeah. But it's just to me, it's elegance. So, we know how to think about the force, molecular force, in the zeroth order. This is, of course, the simple borrowing rubber elasticity kind of concept. In fact, very much still along the way that the tube model assumes, which is the force is coming from intrachain. The interchain does what? It does the uncrossability. It does nothing else. The interchain produces uncrossability, produces the junctions. Okay, so this force is known. Now we just have to deal with the other force. intermolecular retraction force. Sorry, the intermolecular gripping force. And the only thing left for me to say here, let's turn to this page again, is, oh, now you know how to say that. Now, look. Now you really know how to say that. This chain retraction force simply grows with strength in the affine limit, right? So if my strength is affinely is monotonically increasing, my molecules are also monotonically being sheared. This is a linear function of gamma, so it will grow linearly, but it cannot grow forever because what's available is not infinite. Look, this intermolecular gripping force is not infinite. Why it's not infinite? Well, because there is chain relaxation going on. Okay? So this, of course, gives me an opportunity to make a linkage. I just said that the reason this gripping force is finite is because molecules performing its Brownian motion can relax. We'll get to this. We'll get to the formula for this at some point in the near future, how to write this down. But it basically, I may lose my ability to provide the uncrossability since my chains are all moving, okay? However, I want to make a linkage that we already covered. In melt stretching. If you are able to draw very fast, in fact, for example, about 10 times, the extension is just a very peculiar thing. It's all the scales growing exponentially. When I say that, I mean this. So if I write one more time, it's epsilon dot times t, right? And that means it is e to the WIR t over tau r. Okay? When this is 10, my God, if t can enjoy stretching to tau r, that's e to the 10. It's just a gigantic number. Cause and effect. I tend to think this is the cause, but I could be very loose on this point. The bottom line is when you stretch fast enough, we'll come back to talk about even a more perplexing feature, which is this regime 4 type of melt rupture, as you know. Can it happen in shear? Oh, Lord, I'm not going to answer that question now. Can it happen in shear? We only talk about extension, okay? So for extension, we know it happens. So which means what? Which means there is a limit where this force diverges. This force refuses to go away. Okay, you get it? Refuse to go away. That obviously is involving an entirely different scenario than what we are about to talk about so far. Meaning, scenario that chains stretch. I know I use the example of shear, but here is the extension. Chains stretch forever until what? Until it breaks. Okay? So I just want to mention it because we talked about it in chapter, I want to say it's in chapter 11, actually. We actually talk about simulation. Talk about it. So I just want to mention that and then come back to the case where the rate of stretching rate of shear is not very fast, then this force is finite, which means you cannot deform affinely without reaching a point where you cannot deform further affinely. So this is, of course, a punchline. This is a point involving the new physics. It's the force imbalance between these two forces. So this is the whole physics. After 20-some lectures, we reach the final physical picture, force imbalance. This growth has to stop. The rest is for everyone to imagine. If this stretch to a point, it cannot further stretch, what happens next? Well, it's for anyone to imagine. Of course, I have data, so I have powerful data, so I can actually very trivially tell you what happens, which is giving me another chance to speak about what is entanglement. And only then you know what is disentanglement, okay? You know the logic here. If you don't define what is entanglement, you cannot speak about what is disentanglement. And what is entanglement? Entanglement is not like you take a picture, you find your chains are like this, suffering uncrossability constraint. But rather, this constraint fixes you in position. That's entanglement. In other words, entanglement is a dynamic concept. It's not a static picture. When I draw this picture here, you should tell me that says nothing about whether this red chain and blue chain are in entanglement or not. I know I'm confusing you already. Let me clarify. If you like, in that sense, we are speaking about another layer of entanglement. There is entanglement in the linear response sense, in the quiescent sense, where you have a tube-like confinement due to uncrossability. But there's another type of entanglement we're talking about. We're talking about when I stretch, do I still have entanglement? Okay? By that, I really mean, you know for sure what I mean, is when I stretch between the entanglement, can I stretch this strand? Right? That would be another way of defining entanglement exists. When am I unable to stretch? Well, we just said that happens when you have force imbalance. And what does that mean? It cannot stretch further. What does that mean? It means if I move my blue chain further, the blue chain and red chain will slide with each other now. So that's what we mean by disentanglement, and that's also what we mean by entanglement, that there was no sliding. No sliding. I mean, again, zeroth order picture, okay? I'm not going to be able to define anything further. No sliding between chains. Whereas, why you have sliding? Well, it's because of force imbalance, right? Right? So with this scenario, it is very clear to me, and it should be clear to you, about what do we mean by what we should anticipate with respect to a startup. It doesn't matter if it's startup shear or startup extension. That there will be a point of forcing balance. Beyond that, you may say, I wonder why it didn't just level off. That's a legitimate question. That's a legitimate question. How to answer that? I mean, what on earth? This could happen. Why it didn't go through the dashed line? Well, let me try to further confuse you first. Let me confuse you first. You do have the dashed line. Only way I should do justice is draw the blue curve. You do have dashed line. When, in other words, you don't have overshoot. There is no overshoot when the rate of shear is low enough. And you say, well, I said that before. This is still a yield point. I call it unforced yield point, right? Unforced yield. It occurs because of diffusion. So it occurs in this notation. I may better as well just take advantage of this notation. It occurs around Wi, right? It cannot proceed, build more stress by the time you reach the diffusion time. So that's clear. I didn't really answer the question of why this red one why maybe in another universe it does that. I'm joking, of course. That in another universe your polymers don't overshoot. You just keep building up your stress, never overshoot. Who knows? And for us, we can do the reverse engineering, quote unquote. The fact that it drops means when it slides, you start to lose the retractive force. Right? Come on. Your stress is nothing but this. Let me try to be careful. In fact, here you can start to visualize how to think about it now. So what factor is causing this drop? Tell me. The stress drop. This thing drops. Which factor is causing this drop? Well, my question is almost circular in the following sense. You can answer by saying, hey, that depends on how you define retractive force. Okay? If I'm being careful. I mean, we have had a great deal of insight by using rubber elasticity theory. Okay? So I will continue to use that notion of rubber elasticity theory. By doing what? By saying the following. Any of the strand that has not disentangled, has not reached forcing balance. Remember, I should indicate, your strand is a Gaussian distribution, actually. There are different lengths. Okay. So there are strands that has not reached this point. There are strands that has. And this, of course, is capturing the total. So the convenient way to do it is to say, oh, this, I'm going to leave it alone. This only depicts the one that has not reached forcing balance. So it will still further stretch. So this thing is still monotonically growing. And then you know the answer. This must drop. Well, why not? Because the strand, you're losing the density. You're losing the effective strands that are still there. So this thing is dropping. Is perhaps a good way of saying it. And this insight was used in extension, was used for us to realize that we should use engineering stress. I know the comments I'm making only make sense if you could recall what we thoroughly discussed about the case of uniaxial extension and the choices of using engineering stress. That's back in many lectures ago. So, so these are just a bunch of words so far, actually, all I have said. It, of course, emphasizes the point of force imbalance start to remove some of the entanglement strands. Yeah, there were some strands start no longer entangled with each other because they slide. And the remaining ones, if they have not reached force imbalance, may still stretch. But the overall trend is that you start to lose some contribution, and that's how force comes down. So that's not a very difficult point in that sense, meaning not very difficult that this doesn't follow the dashed line, because you start to lose them. Again, my favorite case, this limit, you can never lose them. They're just voluntarily, meaning when one disappears, next one comes back up, meaning they are in equilibrium. This is the weak flow limit. You never lose anything. There's no force imbalance to speak about. There's only the diffusion trying to compete with your imposed deformation. Okay, so with this, with this we covered the startup, if you like, right? We really have covered the case of startup. Startup. I mean, if you start to recall the way we proceeded, you may say, of course, today your book is very thin after the summary, after the review. Of course, we talk about startup both in terms of shear and extension. And I'm not going to even say too much more here that in both cases that the disentanglement can be localized. There will be horse race. We spoke so much about it. We spoke about whether that will give you shear bending or not. Whereas in extension, there's no scaling argument. Once one part is weak, that part will fail. So that's startup. If you follow what we have done, well, you may say there was also laws, large amplitude oscillatory shear. Well, what can you say about it? Well, the only thing I wish to say is I'm against what is said in the literature. It is not good fingerprint. Oh, did I say fingerprint? It's not good fingerprint of your system unless homogeneous stranding is maintained. Okay? This, of course, sends an alarm. Anyone who claims that, okay, let me just say one word. Laws typically means you may have nonlinear response. What does that mean? You actually means your, so let's say it's done in the strand mode. Your stress response can have a subharmonics. In other words, instead of having omega as response, you may have 2 omega, 3 omega, and 4 omega, and so on and so forth. And I have to, forgive me for not remembering it. We had a paper where, at that time, I still remember rather clearly, the even type versus odd type have certain meanings. If I recall, if there is edge fracture, that will give you even omegas. And if there is no edge fracture, you only have odd omegas, or something like that. Don't quote me, but we had papers, I understood that issue before. It certainly means you can look into that. This would be people could claim this to give you a fingerprint, rheological fingerprint, only if you have homogeneous shear. Then we had movies showing it's not. You can have shear bending. Okay? And you have to understand that shear bending is slightly more peculiar, right? You basically shear in one direction with enough amplitude such that the forcing balance is about to occur or has just occurred. But it has occurred, may not have reached horse race, because then you already return. And then you build it again. So after many cycles, things can start to localize. The disentanglement can localize. So it's a very interesting and complex case, if you like. As I was trying to say, if you can invent more way of deforming, let me know. I only know 3 ways. Startup, oscillatory, and step. I don't know any other ways. And then, of course, there are other ways, which is a combination of all the 3. Okay, you can have a combination of them in some way, right, as we did before. Here is where the trouble begins. Meaning, when I say trouble begins, here is where it seems that there is a third force to introduce. Here. There is a third force to think about. So let me just write it down and then I will try to explain. So I call this force cohesion force or entanglement force. I think entanglement force is a little bit more misleading. And we basically don't have a very good word for it. I don't recall, this is all in this paper, right? I tried to, you have to go back to it. I don't recall if I ever called this force a virtual force or not. I certainly remember calling it. I just don't remember whether it was written into the paper or not. Virtue has the flavor of not real, right? In English. Virtue, it exists in some virtual way. And I want to say this force is the most difficult to understand, most elusive. I did something in the book, I'm not going to do it there. I'm going to just try to say a few words before we finish. And this is to answer the following question. So you can have a step strand. Remember, this is very much related to chapter 14 on the so-called finite cohesion issue. You could have a step strand moderate. For example, gamma equals 0.6, for example. And you hold it for a sample that is capable of breaking. So, for example, at 2, it will break. And we have not yet to say why it breaks. Breaks elastically, or we call it elastic yielding. We have yet to say very much yet about this last bit of nonlinear rheology yet. But in contrast to that, at 0.6, nothing happened, the very same sample. So the third force was recognized or was introduced to account for that. To the fact why there's a threshold, why there is a finite cohesion, why this cohesion is not zero. Remember, according to the tube model, this cohesion is zero. In other words, it cannot tolerate any amount of step strand, because any amount of step strand after Rawls time will witness chain retraction, which means the structure the deformed structure undergoes some change. Where we showed in chapter 14, at least as a rheological measurement, such a structural change due to Rawls would have produced some rheologically, some experimentally measurable rheological consequence, but we didn't see it. So this lends more support to the proposal that there is a third force called cohesion force. Excuse me. I think this is a point so much related to the idea or unrelated. It depends on your perspective. I know this is so much pertinent to the problem of Rawls retraction. So let me explain. I know you can hardly see what I did, right? So this is one of the tube. This is the other wall of that tube. Okay? Not only we typically draw a tube very straight, not so wavy as I draw here, but also very smooth, very much unlike a Gaussian chain. So remember, I remember you asked that question. So the question related to that was whether that Rawls retraction can be barrier-free or not. So it's the same question. And the insight we have is not barrier-free. There is a barrier. What barrier? The barrier that if you want to hurry, imagine this black chain, somehow is already stretched and black chain trying to retract. Since the tube model is arbitrary, it like to visualize, my chain lives in a tube, in a real tube, a smooth tube, and the chain just like a snake just try to retract along the tube and come back without any barrier. But such a picture doesn't really exist. If there is a fast retraction of the chain, its conformation has to change along the way of retraction that other chains will not allow it. Okay? So in any case, I think this is as difficult a point as I can make it, that we're saying there is a force exactly of this level. That's the third force. You have seen it. You have seen it. This third force is the unit of that retraction force. When I say unit, because it's just the elements, it's the elemental, right? It's a measure of the amplitude of that. The rest is dependent, of course, on how much you stretch. So suppose you deform 60%. Okay, what does that mean? It means you produce a retractive force which is 0.6 of this. By definition. Right? By definition. And the idea was I have this much of force available to keep it in check, to keep it balanced. The chains after 60% deformation have no way of fighting to retract or to disentangle or to reach force imbalance. Because what's available is larger. Meaning, we propose it's on the order of this. So this really is the least obvious thing I could say and do. And really, it's up to you guys to find a better way to think about it, or maybe. But this is, I think this brings us close to today's lecture. Okay.